Okay, beats. Beats are also called wah-wahs. Okay, so if you play in the orchestra or the band or something like that, beats are called wah-wahs, and that's when you're playing a pitch and somebody else is playing a slightly different pitch, you'll hear these wah 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 sounds like that. And I'll demonstrate this, but the basic idea is if we've got, say, a lower frequency, 50 hertz and 60 hertz, right? You can see that at first we've got constructive interference. That is, we add these up, right? Later on, we'll get destructive interference, and then later on, we'll get constructive interference, and then later on, destructive, et cetera, right? And so what you tend to hear is the envelope of this, right? It's like a amplitude modulation, okay? It gets loud, soft, and then you hear kind of an average frequency like that. And it's cool. I've got some demonstrations of this. But the very best demonstration won't be with like the speakers. If we can get a couple trombones, get them in tune, and that's a trick sometimes, right? Get a couple trombone players to play in tune, get a snare drum, put it next to them, and then just have one of the trombones just slide that slide out a little bit or pull it in a little bit, and you can get the most amazing beats. But I've got some good demos of this. The formula for it, though, is very, very complex. The beat frequency is just the difference in the frequencies. Okay, so for example, if you've got 228 hertz and 226 hertz, you're going to hear 2 beats per second. Okay, and the absolute value is just if you're unclever enough to subtract the larger from the smaller. You don't get, there's no negative beat frequency. Okay, let's look at some of these here. Okay, I play a pitch of 256 hertz on my penny whistle. You play 384 hertz on your whistle. What's the beat frequency? Well, let's figure this out. It's just going to be F1 minus F2, right? So the absolute value of 256 minus 384, right? Minus 384, and that's 128. Now, the interesting thing is that 128 hertz is a frequency that we can hear, okay? And let me also suggest that 128 hertz is actually the C below this, which is interesting, right? Because an octave is just a doubling of frequency, right? So 128 hertz is a C. If you double 128, you get 256. That's also a C. By the way, 512 would be a C. And then that 384 is the G in between. So you can see that this series of notes is actually part of a chord structure. And the reason that a C and a G sound cool together is that they generate an undertone, right? And the undertone is part of this whole chord sequence. I'm sorry if you're not a musical person. Your eyes are glazing over, but this is cool stuff. Okay, and then the cool thing is that the penny whistle generates these frequencies naturally. Okay, it produces 1 F naught, 2 F naught, 3 F naught. So this might be the high C that I can play. This might be the low C that I can play. I don't think that's true, but right. And then if I keep playing, I'll get a G, I'll get a C, and the next note will be an E, then a G, then a kind of a B flat jazz tone, and then I'll get a C again. Okay. Okay. Wow, tangent. Okay. I'm playing 384 hertz. I hear a beat frequency of 310. What are the possible other frequencies that are playing? Well, basically the question is F1 minus 384, right, is 10, right? And the two answers are that I could be playing 394 hertz, right? That would give you 10, right? I could also be playing 374 hertz, okay? It could be below that or above that to get a beat frequency of 10 hertz, okay? All right.